Hello, everybody. Thanks for joining us. Let's wait for a couple of people to log in. Thank you for joining us today. We're going live on YouTube as well, but for those who are joining us live, you can certainly participate.
Hello, everybody. Thanks for joining.
All right. Okay. So I'm Jenny Chen. I'm the founder and CEO of 3D Heals. Everybody knows this speech already. And I founded 3D Heals about 6 years ago with the purpose to discover, connect, and educate the public. And my own personal goal is to discover innovators and startups because I find them extremely interesting in the space of healthcare 3D printing and bioprinting. And we are organizing a series of this kind of webinars because of pandemic, we can't really connect people in person. So this webinar is in place of that. So we have this very amazing panel of speakers today, focusing on very important subject. And after the presentation, we'll also invite everybody to go to the breakout room on Zoom, which I sent out a link last night in email, where you can find the link. And later I will also share the joining information in the chat box. Meanwhile, please feel free to say your name, where you're from, and what you're looking for in this webinar. And for your questions, please enter your question in the QA box. And I'm going to be the fly on the wall after saying this. But I also want to make an announcement that I want to thank the sponsor for this event, which is HP. And HP has graciously and generously offered to sponsor our next 20 events as the anchor sponsor, because they also want to do exactly the same thing that we do, which is discover startups, innovators in the space, obviously with a corporate strategy behind it. So without much delay, I want to introduce a moderator of the day, Leanna Sanders from Advanced Solutions Life Sciences. She is our moderator of the day, so I'll let you take away, Leanna.
Thank you so much, Jenny. Thank you for the opportunity to moderate the session today. As she said, I am Leanna Sanders, and I have been in the bioprinting field for just over 5 years now, working at Advanced Solutions Life Sciences, where we develop enabling technologies for bioprinting and biofabrication. And personally, having a background in cardiovascular regenerative medicine, and with my current passion around tissue engineering, I am really excited to hear about the innovations and insights of our panel of experts around what really is the holy grail to regenerative therapies, which is tissue vascularization. And so today we have 3 outstanding panelists that will each provide a brief presentation, followed by plenty of time for questions and discussion. And so as questions arise, as Jenny mentioned, feel free to submit those in the Q&A panel, and I will work to get as many of them answered as possible. And so with that, let's get started. Kicking us off today, we have Andrew Hudson. Andrew is the co-founder and chief operations officer at Fluidform, where he leads the development and scale-up efforts of their life support biomaterial or bioink product, and is also amazingly completing his thesis work at the same time in the Dr. Adam Feinberg lab at Carnegie Mellon, where he focuses on next generation techniques for vascularizing 3D bioprinted tissues. His work was also recently featured in Science, and he personally contributed to significantly improving the resolution of the fresh technique. And so with that, Andrew, the floor is yours.
Thank you so much. Can everyone hear me all right? Hopefully everything's working from a tech perspective still.
Yes.
Cool. Well, thank you so much for having me for that introduction. I'm Andrew Hudson. I am both a co-founder in Fluidform and, as was previously mentioned, a PhD student in Adam Feinberg's lab. But today I'd really like to talk about how Fluidform is using Fresh as a biofabrication platform to try and 3D bioprint vasculature. So a little bit about myself, as I've already stated, and with the introduction, I'm both a PhD student and a co-founder of Fluidform in Adam Feinberg's lab. And a lot of what I'm talking about today, as previously mentioned, was published in Science a couple of years ago, back in 2019, where we really talk in a lot of detail about using this fresh technique to 3D print, specifically collagen bioinks in the context of cardiovascular regenerative medicine. And a lot of my co-founders are also on this paper. So it's really nice that we have a lot of people in the company who have tremendous expertise in this area in 3D bioprinting, working alongside me every day. It's really, really fun. But with that, there's this huge attractiveness to tissue engineering as a potential for not just cardiovascular regenerative medicine, but a lot of other organ therapies as well. And the reason for this is that tissue engineering sits at this really interesting intersection of using a patient's own cells, engineered scaffolds, and other biological factors to try and generate therapies that also have a chance of integrating and growing into a host instead of just trying to be biocompatible like a mechanical heart valve where you take blood thinners. People are trying to make heart valves that actually are made from a patient's tissue that actually grows into the patient over time so that you don't need to take things like long-term blood thinners. Unfortunately, there's been very few tissue engineered therapies that have made it into the clinic. And there's a lot of reasons for this, but a lot of what you see today from what you could say is kind of a tissue engineered therapy, they really rely on the host to generate the tissue almost entirely, with the example of a cabbage, where you're really just taking a saphenous vein from somewhere else. You're really relying on pretty much the entire body to have pre-made something for you, and you just kind of transplant it within the patient. So the question becomes, well, where are all these engineered organs? And that brings us to what we're here to talk about today, which is that vasculature is really the main roadblock right now in tissue engineering very powerful therapies. So vasculature is really, really challenging to build, and there's a lot of reasons for this. The first one is obvious, it spans many length scales from the aorta down to a microvasculature capillary bed and then back up. It's not just doing this in 2D, it's doing this in 3 dimensions all at once. So you can see if we have, for example, a liver vasculature rendering, it's this immensely complex branching 3D network. And it's not made from rigid metals that can be made from lithography. It's made from very, very soft materials that are also undergoing constant remodeling. So it's very dynamic and very challenging from an engineering standpoint. So the question is, well, how can we start to create perfusible vessels in the context of vessel engineering? And a lot of what other people have done in the past is, for instance, used decellularization and recellularization. The advantage here is that you get really, really nice ECM and the microarchitecture preserved because nature kind of already generated this for you. The difficulty then becomes reintroducing cells precisely into their own locations again, especially multiple cell types. It's really, really hard to precisely reintroduce them because the cells are so much larger than these cell fractional pieces that have been washed out with detergents. And another method that people have used a lot are things like microfluidics, where you have this beautiful 2D architectural control, but they're using materials like silicones or other plastics, and they're 2-dimensional, and they're not really replicative of the ECM or extracellular matrix in the body. So we really start to ask at Fluidform, can we try and merge the advantages of each of these to build 3D ECM-based vessels precisely? And a method that we're really attracted to doing this with is pretty obvious by now, is 3D bioprinting, which I think still has really, really untapped potential. Pretty sure everyone here is familiar with how 3D printing works. So you have the sequential stacking of little thin cross sections, in this case, printing a little robot. But you don't just have to print a robot. This robot could have been injection molded. 3D printing allows for the generation of immensely complex mathematical surfaces or other things like this gyroid lattice that you really cannot make through traditional casting or subtractive manufacturing techniques. A huge challenge becomes when this plastic becomes applied in a biomedical context with soft proteins. And what ends up happening is that all these soft biopolymers are really mechanically difficult to print, especially in open air, and they end up collapsing on themselves. So a lot of what has been in the literature for the past 5-10 years have been these orthogonal log pile structures that are kind of a couple centimeters or maybe a couple millimeters or a centimeter tall. They rely on a lot of things like thickening agents to provide them some structure. So a barrier that 3D bioprinting has run into is that printing soft materials is really, really challenging, especially when you want to print them in complex manners. To address this, the Feinberg Lab and now Fluidform is using a technique that has been developed at Carnegie Mellon University called freeform reversible embedding of suspended hydrogels, or FRESH. And this is kind of our main piece of technology that we've been publishing on for the past couple of years. So if we have, for example, a picture of a finished product printed in FRESH, in this case, our company logo, there's a couple of major pieces to a FRESH printing. The first is just your standard extrusion ink. In this case, I'm using an alginate ink as an example. You obviously have your needle that dictates your print resolution, your printed object that's pretty standard from anything like CAD. But the most important part of the system is this support material. So we do not print in open air anymore. We actually temporarily embed inside of a sacrificial support material. The support material has one really important physical property in its rheology, in that it has a yield stress. So at rest, it behaves like a solid. Under shear, a critical amount of shear, it starts to flow like a fluid. So it's a lot like hair gel at the grocery store, where all those air bubbles are kind of temporarily trapped in the hair gel. You can squeeze the bottle, the hair gel and the bubbles start to flow out of the tube. You stop squeezing and they go back to kind of being trapped. So we have this material that can transition back and forth between being kind of like a solid and kind of like a liquid, depending on how you're shearing it. So wherever the needle is moving through this bath, the bath is moving out of the way like a fluid and cushioning the material that's temporarily injected and printed inside of it. Oops, sorry. Sorry about that. So the support bath is made from tiny gelatin microparticles that are around 30 microns large. And these materials from gelatin, they can be melted out at the very end. The print obviously cannot melt at body temperature, in this case, alginate or collagen. So these parts are very easy to remove because you just raise the whole print bed to body temperature and you're able to retrieve your print. So when we put this all together, in the case we're printing alginate here as an example, it's easy to see because it's been dyed blue. Alginate needs divalent cations to gel. So in that case, we just mix a little bit of calcium into that bath ahead of time. And here at the very end, we've raised that whole print to body temperature 37°C, and it very slowly melts the gelatin. So you have this really nice, delicate, gentle release process on these really delicate bioinks that are normally very mechanically weak at the very beginning. So like I said, we have that gelling fluid ink temporarily embedded into the support material, and the whole thing's melted. So with Fresh, we can really start to print for function. We can print almost any gelling material, and we can really print in any geometry. If you look at the fluid form logo, you have these 90-degree overhangs, but you don't have to print any support structure under them because you're printing inside of a ubiquitous support material. So that whole technique of Fresh, we initially published in 2015. We essentially improved the resolution by an order of magnitude, and we were showing that we can print things very powerfully out of collagen. We published that in Science in 2019. So if anyone's interested in really learning about Fresh, I really recommend reading these two papers in particular. And this whole IP portfolio has been wrapped up and licensed to Fluidform exclusively from Carnegie Mellon University, and that's a lot of what our methodology is based on. But with Fresh, we really have these basic building blocks of fresh printing collagen. So in this case, it's really just dictated by how small of a needle are you using. We show that we can have down to 20 micron filament resolution. That's with a really small needle, obviously. 80 microns is very typical. We're showing that, hey, we can pack these things together just like a plastic FDM printer would with collagen. We can stack them vertically, and we can have everything look exactly like how a printer or computer slicing software would want them to look, which is really nice. We get great matchup between the computer-generated slicing and what we actually see in real life. We can change the variable spacing of the filaments, and we can have all this type of 3D architecture like you would just in plastic. So we have this really powerful platform to print, in this case, collagen specifically, in really almost any shape that we want, just like you would with a regular plastic printer, but we've been able to do that thanks to Fresh. So in the case of vasculature, for one, we can take something like patient-derived MRI data. So we have, in this case, an actual patient's right coronary artery that we were able to find anonymously online, so it's not tied to anyone. But we undergo the same fresh printing process here. And again, the main concept is that a collagen ink is first acidified in order to be solubilized. If we print into a bath that has, in this case, not the calcium that the alginate needed, but is neutral and pH buffered, that neutralizes the acidic collagen as it's printed into the bath. And so we're able to print this little collagen arterial model right here. So we have all those little microparticles providing support, and they can be melted away. So we have that MRI data. We can print it out of collagen. We get really, really high fidelity between the model and the actual print. And what's really nice is we can show that we can start to perfuse these things. And that what's very interesting is that the really, really nice fluid diversion in this is because this is how the fluid would be diverted in the body based off of things like Murray's law, the angle of the branching, the diameters of the daughter branches, everything just gets copied from nature. And so obviously it's able to divert fluid really, really beautifully. So we have an entirely biomimetic design process essentially for this case of bioprinting. But we don't just have to use MRI models. There's a little bit of a limitation to MRI because it can only get vessels that are so small. So again, we now have that patient's heart that we had used to get the coronary artery from the previous slide. We have focused on, in this case, the left ventricle. And what we did here is that because we only were able to get the very, very large arteries that were able to supply the heart in this case, we didn't have anything below a couple of millimeters in diameter in terms of the vessel size. So we took those vessels and we actually used them in combination with a computer algorithm to kind of fill in the gaps. So those dark crimson lines are the ones that actually came from the patient, and all those things in kind of the green, the yellow, and the blue were generated by an algorithm where it branches more and more. Every sequential branching, the diameters of the vessels get smaller and smaller. So again, here in the red is what came from the patient. The purple is what a computer generated. And we've kind of taken out this little pink slice that we were interested in printing in this case, just to show that we don't have to print like this huge thing. We wanted to print a little portion of it because it's more manageable. So we have that model that's a little bit of patient, a little bit of computer generated vasculature. And we were able to just print this with very high replication and fidelity thanks to Fresh. And what's neat here is that if we chemically do a little bit of treatment on here to optically clear that tissue, so we can look deeper inside of it, we can also perfuse this just like that right coronary artery before. And we show that we get really, really nice fluid diversion even when we go from the patient data to the computer generated data as well. This again is entirely 3D printed, entirely from collagen, really like no methacrylation or anything involved, but we're getting really complex 3D branching vessel networks thanks to Fresh. So that was an instance of using a little bit of computer generated modeling. We can also just do entire computer generated models. So we have basic CAD structures. In this case, we have a little vessel going through a block that is entirely man-made. Just like the other ones, we're able to print this with very high fidelity from Fresh. And we show that with this little tiny vessel, if you cast cells into that little tiny well and chamber in here, but you don't perfuse anything, unsurprisingly, the cells that get casted into that well below this air-liquid interface all just start to die over time. That's not very shocking. So you have this really thin film of viable cells near the surface, everything else dies. But when you're perfusing these tissues in these little vessels, you get drastically increased cell viability. They're alive long enough to actually start undergoing cell-driven compaction of that tissue, which is a really good sign that they're alive and happy. And we do show, we analyze from as a function of depth, that as you get deeper into that tissue, the one that's been perfused is significantly more viable, whereas the one that was statically cultured has died. So any attempt to make thicker things, you're going to need perfusable little vessels, and we show that we can at least start doing that with Fresh. So we've shown with Fresh, we have this big flexibility of our vessel design structure. So we can go from entirely patient-derived MRI data. We can do the exact opposite, where we do 100% CAD. And we can do something that's in the middle, where we kind of have this hybrid model that is bio-inspired, but then supplemented with computer-aided design. There's also the huge importance of microvasculature, which is really, really difficult to engineer. What we've been able to show previously is that all of those things that are printed with Fresh have a little bit of porosity to them. They're actually around 75% porous because those little gelatin microparticles that make up the bath act as a porogen that gets removed when the bath gets melted away. So we have all of these structures